I think we'll get started. Welcome to the Oxford Climate Research Network annual lecture. My name is Helen Johnson, and I'm the current convener of the Oxford Climate Research Network, or OCRN. For those that don't know, OCRN is one of Oxford's 5 networks for the environment, and it exists for anybody at the University of Oxford with a research interest related to climate. And the goal is to help make us more than the sum of our parts, to help us take advantage of opportunities to work across disciplines and to better project what we do both within Oxford and beyond. So if you're not already on our mailing list and webpage, you can find out how to do that from the webpage, and I encourage you to do so. Our annual lecture is one of our biggest events of the year, and very much looking forward to hearing about what we can and can't know about the impacts of solar geoengineering. But before we dive into that, I just wanted to take the opportunity to advertise another OCRN event coming up in 2 weeks' time. On the afternoon of the 17th of March, we're hosting a forum around climate and health, where we'll hear from some funders in that space and a handful of people at Oxford already active in that space, both on the mitigation and the adaptation side. And the goal is to develop a shared understanding of kind of current and emerging funding opportunities, and to start to coalesce around potential shared initiatives and joint bids. So if that sounds appealing, you can find out more details on our webpage, and I'd encourage you to sign up. Without further ado, I'm going to hand over to Professor Miles Allen, who's going to introduce our distinguished 2026 OCRN annual lecturer.
Thank you very much, Helen, and thanks, Melissa and Helen, for organising this. It's a huge pleasure to introduce Dan Schrag, and it's great that we've been able to take this opportunity of him visiting Oxford to give us our annual OCRN lecture. I've met Dan quite a long time ago. I guess in the early 2000s we worked out. Dan's career can be briefly summed up as Yale, Berkeley, Princeton, Harvard. That'll do. Did I get it right? I did. Okay. And he has been, and actually, but in Harvard, he's been in geosciences, but now has 1 foot in the Kennedy School of Management, which is Kennedy School of Government. So his interests span both the physical science of climate and its policy implications. Since he's talking to us about geoengineering, I can't resist observing that my first encounter with Dan, so to speak, was his paper with Professor Hoffman on, Doug Hoffman, I'm not quite sure if he was a professor at the time, on snowball Earth, which you might characterize as the ultimate termination shock. So on that, Dan's going to tell us about geoengineering, solar geoengineering, and we're hoping for plenty of questions afterwards for a discussion as well. So thank you, Dan. Thank you for joining us.
So thank you. So it's lovely to be here back in Oxford. Oh, this is very loud. It's very loud. I'm going to lower it a little bit. I'm pretty loud anyway. I'm actually giving another talk in Earth Sciences on Friday, a little bit more about the snowball, but very different time scales. Hold on, does it? I think I'm just not figuring out the clip. Let's figure it out. There, is that better? Okay. So it's nice to see everybody, and I hope we'll be able to have a vibrant discussion. So this is the title that I emailed my wonderful hosts when they asked for one. It's not quite an accurate description. It's part of what I'm going to talk about, but it is. I am going to talk about something about whether we can know the impacts of geoengineering and why it matters. I chose this topic because this is a subject that I actually haven't worked on that much, but it's something that I was very interested in a long time ago, soon after Paul Crutzen wrote his famous paper, which was, I guess, 2006. So here is just a cartoon reminding people what it is. I'm not going to do a lot of background here. There are lots of different approaches to solar geoengineering. I'm going to focus for now on the idea of aerosols, being deposited in the stratosphere, and they would basically reflect sunlight and cool the planet. There are lots of different ideas about the details of how to do this. We'll maybe talk very briefly at the end about space as well. I'm not going to talk about some of the near-Earth things like marine cloud brightening. They tend to be more local. They're also very short timescale interventions, and for reasons that I think will become immediately obvious, the timescale of this really matters. And just as a reminder, when you put aerosols in the stratosphere, the timescale is about, depending on where you put them, 6 months to maybe 2 years. This is just a schematic, and cartoons are very dangerous. I'll remind people of that. This is the Brewer-Dobson circulation in the stratosphere, essentially large cells that go from the tropics out to the higher latitudes. And the higher you put the particles, the longer they will last, the longer path they have. But again, cartoons are problematic. It's a little bit, it's a lot more complicated. And in fact, our understanding of stratospheric circulation still could use a lot of improvement. A nice example that is often cited is Mount Pinatubo in the Philippines that erupted in the 90s, depositing a fair amount of sulfur into the stratosphere. And this just to give you a sense of what we're talking about, this is a satellite images of optical depth, looking at optical depth. This is here. This is first one is before the eruption. This is after the eruption, because the Philippines is on the equator. You see particles being mixed very quickly, sulfate aerosols forming and mixing very quickly east-west. So the zonal mixing is very, very fast in the stratosphere. And this is a little bit later. So this is June to July. Here's August to September. You still see more dense particles in the tropics, but we're starting to get them all the way to high latitudes. And this is actually a couple of years later where many has dropped out, but you still have some residual brightening of the stratosphere. Just gives you a sense of the processes as they played out after the Pinatubo eruption. I got interested in this, and the person who had been thinking about this a lot was a guy named David Keefe. David at the time was at Calgary, and David and I together convened a meeting in November of 2007 at the American Academy of Arts and Sciences in Cambridge. And these are I started the discussion. There were about 40 people. They included my friend Ray Pierre Humbert from the University of Chicago, now here at Oxford. A lot of other really interesting people, lots of very good climate dynamicists, George Philander, Mark Kane, many others. And these were the questions. How do we do it? What does it do to the climate system? What might go wrong? Does it postpone the need to reduce emissions? And a slightly separate question, will it postpone the reduction of CO2 emissions? Who controls it? That's a really big issue. And then when should we start, if at all? And what do we need to know before we start? Seems like a long list of questions. I was involved in recruiting David Keefe to Harvard. He was there for a long time. He just left a few years ago and is now at Chicago running a program on climate engineering, which is mostly focused on carbon removal, but I think there's some solar geoengineering issues as well. As I said, my friend Ray Pierre Humbert was at this. Ray and I had actually worked together on some Snowball Earth related stuff and actually some stuff on the early climate of Mars. Ray, as you probably know, hates this subject, like passionately hates it. He just gave a talk a few weeks ago online about this, and he thinks it's almost like he has to spit when he says the word. I love Ray, and we're old friends. And so I partly chose this topic to talk about here because I had hoped he was going to be here and we could actually have a dialogue about this. That was when I was sad. I got an email from Ray saying, I see you're giving March 4th Oxford talk. I'm at MIT continuously through June. He's now half-time at MIT. But he'd like to get my thoughts. I see you're starting to have reservations, though I know you were, at least for a time, a proponent of David Keefe's research. He misunderstood my title, as I'll show you in a little bit. I told him, as far as the solar geoengineering, I believe you and I are still very far apart. but I hope you will appreciate that I'm coming at this with a serious and earnest analysis of the climate system, but also the energy system and the political systems of the world. So let's talk sometime on geoengineering. I doubt we will agree, but I would hope we can respect each other. And Ray responded, well, disappointed, because I thought maybe you had finally seen the light. He actually originally, in his first email, he had encouraged me to write a Guardian article the way he and Mike Mann had. And I want to talk about that and use in some ways, and it's a shame Ray isn't here, but if it's being recorded, he'll probably watch the recording. I have so much respect for Ray, and I want to talk a little bit about why this tension exists and why this disagreement exists, and see if we can try to understand that a little bit. So this is from 2021. Ray and Mike Mann wrote, actually I've written a couple of Guardian pieces, but this is the first one that came out. And this is the beginning of that piece. He says, while it is certainly true that reducing sunlight can cause cooling, it acts on a very different part of the climate system than carbon dioxide. That's absolutely true. Reflecting shortwave doesn't seem like it should actually compensate for long wave radiation. First of all, there's a time difference. Greenhouse gases affect infrared radiation all the time, 24 hours a day, whereas increasing the Earth's albedo only matters when the sun is shining. It doesn't matter at night. But he also says, an efforts to offset CO2-caused warming with sunlight reduction would yield a very different climate, perhaps one unlike any seen before in Earth history, with massive shifts in atmospheric circulation and rainfall patterns and possible worsening of droughts. That's a scientific assertion. What I'm going to try to do today, and by the way, I haven't actually told you how I feel about solar geoengineering. At the very end of the talk, I will tell you how I feel, but I'm going to try to step back and say, okay, let's try to all be scientists here, or scholars at least, and analyze this before we introduce our own personal feelings about whether we like this or don't like this. I think you'll see there's a lot of really scary aspects of this, but let's try to think about it critically. So are there these massive shifts in atmospheric circulation? Early calculations, and this is an old paper, I think it's 2008, by Ken Caldera and Lowell Wood. Lowell Wood was a protege of Edward Teller. Anybody knows who Edward Teller was, that should give you pause to think about this by itself. But what they're showing here in the upper panel is a doubled CO2 calculation from a climate model that Ken Caldera ran. And then the bottom is a doubled CO2, and then they turned the solar luminosity down 1.8%. And what you can see is that, lo and behold, it doesn't look as bad. That's not a huge surprise. But remember, the physics of this is not totally intuitive. I actually didn't think it would compensate very well. My intuition was, if you actually reflect sunlight instead of having the greenhouse gases, or compensating for the greenhouse gases, the compensation would be really bad. And in the beginning, that was my interest in this. I'll give you an example. I had a student named Katie Dagan who now works at NCAR, actually, for now anyway, depending on what happens with NCAR. For those of you who don't know anything about how plants deal with moisture, so leaves of plants have holes called stomata, and they can open and close them. And they have to keep them open because that's how they get carbon dioxide into the plant for photosynthesis. But if they keep them open, they also lose water. They transpire water more quickly. And so in general, plants, if you grow them in higher CO2 conditions, they tend to close their stomata to keep the water in because they don't need to have them open as much because the CO2 in the atmosphere is higher. Okay, it's a basic physiological effect. It basically is often referred to as water use efficiency. And so with higher CO2, plants become, they essentially transpire less. I thought this was interesting. And so as CO2 rises, most plants reduce their water loss, closing their stomata. And that's partly balanced by the effect of warming on the plants, requiring more transpiration to cool their leaves. But in a solar geoengineering scenario, think about it. If you had high CO2 and you try to adjust the temperature downward by reflecting sunlight, the plants are now growing at a similar temperature to what they're existing today, but they're growing in a high CO2 environment. And so they close their stomata more, and so they transpire water less. So it's asymmetric. And to me, that was the interesting part of solar geoengineering. Where does this break down? Where does this not compensate? So we hypothesized that this might cause a big change in the hydrologic cycle, particularly in places like the Amazon, where transpiration of water really matters. So we actually explored this in this paper in 2016, Journal of Climate. Turned out it was a minor effect. Hunch was, boy, this is going to be the Achilles heel of solar geoengineering. Turned out it was actually pretty minor. But to me, these are the kind of issues, mechanistic understanding that we actually need to promote of this. I want to show you a variety of studies that show that actually this compensation of short wave for long wave is actually better than I thought it would be. Here is an analysis from Doug McMartin from a few years ago. So you have here, what he's showing here is that the distribution of temperature changes from a climate model scaled to a 1 degree global average temperature change. So for a global average temperature change of 1 degree, this is just that. You see that parts of the Arctic are warming by 3 degrees. A lot of the continents are warming by 1.5 to 2 degrees. And the oceans are a little bit less than that. And then this is P minus E, precipitation minus evaporation. You can see really big changes. Here, this is the SRM scenario. So this is essentially that, again, scaled to 1 degree of global warming average. And you can see that this is dramatically reduced for sulfur injection. Not perfect, but note that the scales here are different. So this is 3 degrees going down to -3. This is 0.6 degree going down to -0.6 degree. So these anomalies here look big because they're dark red, but they're actually pretty small. Okay? So the compensation is actually remarkably good. And again, the same is true for the precipitation minus evaporation. These are, in this case, it's only half the scale. So the big anomalies that are red are like 0.2 millimeters per day. Here, they're like 0.4, 0.6. And there's a lot of recent work. This is just a reminder for me to mention it. Lots of people are doing these. This is a paper that was done. David Keith collaborated with Kerry Manuel and Gabe Vecchi from Princeton. And they looked at hurricanes using a high resolution model and found that in general, reducing the warming with solar geoengineering reduces the hurricanes. So all of the, basically, whatever effect warming had on extreme storms, solar geoengineering reduced it. And that seems to be the pattern from all of these. I want to show you also that when you read papers about solar geoengineering, you have to do it very critically, because often what you can't assume is that the way somebody imposed solar geoengineering in this climate model is the way we would actually do it in the real world. And this paper is a nice example. This is from Alice Wells. And what they did is they did 2 different injections. They basically did the high emission scenario, IPCC, the SSP 8.5, and they compared it to the low one, to 4.5, using 2 different injection scenarios. In one case, they injected at 10 north and 10 south at 18 to 20 kilometers. And the second, they used 4 different injection sites, 30 north and south and 15 north and south, a little bit higher altitude, 21.5 kilometers. And they used an algorithm to try to control surface temperature, interhemispheric gradient, and also equator to pole gradient. Okay, so the model is running and they're doing a dynamical control where they're adjusting the injections to try to keep those things as constant as possible. And let me just show you what these results look like. So the upper one here, that's the scenario where you just let the world warm. That's the SSP 8.5. They actually subtract out the SSP to 4.5, but that's okay. And then what you see here, that's the warming. And then in both of the geoengineered solutions, you get pretty constant global mean temperature, and the interhemispheric gradient is pretty good. Although the big difference is in the equator to pole temperature gradient. The red is the control one, where they do multiple latitudes and try to keep that constant, and you see, sure enough, that works. Whereas in the blue looks a lot more, the equator to pole temperature gradient looks a lot more like the warming scenario. And you'll see why in just a second. So here is the simple inject at 2 latitudes and just focus on global temperature. And what you see is that the high northern latitude still warms significantly, and that's why the equator to pole temperature gradient is increasing. On the other hand, this is the control scenario, and you can see it's substantially removed when you do this. So there's more sophisticated ways of doing this. It's not simply just turn the sun down, which we can't do right now, or inject sulfur at one location. There's actually a lot more control. And by the way, just note that the scale here, these temperature anomalies, although they look big because of the colors, they're not actually that big relative to warming, right? They're relatively small. And if you actually look at regional temperatures, what you see is this is the SSP 8.51. The sulfur is the one that's a simple injection. And then the pink is the control one where they try to actually control these gradients. You can see they actually improve things dramatically. I think that's interesting in terms of how you read some of these papers where they use climate models for these sort of simulations. I'll tell you what I conclude from reading all of these different papers that have looked at this phenomenon so far. There's no indication yet that what Ray calls massive shifts in circulation and rainfall patterns and possible worsening of droughts will actually occur. That doesn't mean to say we can say it won't occur. It just says that based on all the modeling that's been done so far, there is no indication that the risks of really undesirable extreme weather will actually happen. In general, if you do this, the impacts of climate change will be reduced. Whether it's high resolution models that Kerry Emanuel ran for doing hurricanes, or whether it's various other types of simulations. And my understanding is, Miles, your group is going to start looking a lot at some of the high resolution weather models. That's wonderful. I suspect you're going to find the same thing. That essentially, if you cool the climate, the risks, some of the extreme weather events will reduce. That isn't to say there won't be a mechanism, but I want to remind people that doing this is really hard. And that brings me to the next point, which is regional impacts of solar geoengineering, which is what everybody wants to know. I think they are likely to be essentially unknowable beyond the general warming trend. And when I say unknowable, what I mean is it's going to be very difficult for us to actually predict with any degree of accuracy how any particular region in the world is going to respond differently from another beyond the general warming trend. That is, there is a general warming trend, and we know that it's going to be stronger in the Arctic than it is going to be at the equator. There's a general spatial pattern to that. But in terms of detection and in terms of forecasting, it's going to be actually very difficult to ever know this. I was at a meeting in South Africa last May, and lots of climate modelers were there saying, oh, we need really good models so we can better predict how rainfall is going to change in Ghana if we do solar geoengineering. I actually think that, at least using the current generation of models, that's never going to happen. We're never going to actually be able to say that Ghana is affected differently than pretty much anywhere else. I cite this quote. This is attributed sometimes to Niels Bohr. It also is sometimes attributed to the Yankee catcher Yogi Berra. Oh, sorry, Mike. Oh, thank you. But it's important to have some humility about predicting the future. But I just want to show you how difficult this is. So this is results. Sorry, it's a complicated figure, but I'll try to show you what it is. This is from Daniele Visione, who's at Cornell. He's a modeler who is part of the Solar Geoengineering Model Intercomparison Project. And what this shows is 6 different GCMs. The results for essentially 2 scenarios, a sulfur scenario and a solar scenario. And what those are, the sulfur is where there's actually injection into a model, so a radiative forcing field based on a sulfur injection experiment into a transport model for the stratosphere. And the solar is just turning down the solar insolation. Okay? So it's more uniform. And in many of these, you see that difference. In some of them, you see the sulfur one has big warming in the northern high latitudes, although some of them don't. And you see largely that disappears where you turn the sun down. Again, this is a single sulfur injection experiment. This isn't like trying to compensate for that by adjusting your injection in any way. So perhaps you could get rid of this kind of anomaly. But anyway, what I want you to focus on, though, is if you look at any one place, I mean, so for example, here you get a warming in this model over the Amazon. It's stronger in this one. It's a cooling in this one. It's all over the place. That is, at the regional scale, the difference between models is larger than the kind of signal you get out of them. I'll give you another example of this. This is a paper about the timescale for how long it would take to detect the climate response. And so what they're looking at is a relatively modest emission scenario where you inject starting in 2027, try to stabilize at 1.5 degrees, and then you actually look at temperature and precipitation. This is the timescale to detect whether you've actually made a difference regionally. Do you actually know that you've actually seen it? And what you can see, this is the timescale for the detection. You can see is that it's a really long time starting in 2027. That is one standard deviation, mid-century for some places, but a lot of places not even in 2100. And that's because the internal variability of the system is so high that actually figuring out regional differences and attributing them properly to solar geoengineering, if we actually did it, is really hard. So Tim and I had lunch today, and we were talking about whether this could be done with a much better model that actually properly captured large sources of internal variability in the climate system, things like El Nino. I think it's important to remember this is actually true for climate change in general. That is, if you ask, how has the 1.5 degree warming we've experienced since pre-industrial affected El Nino, the largest source of interannual variability? The answer is, we don't know. If you ask, how has the 1.5 degree warming affected the monsoon in India? The answer is, we don't know. I'm not saying that solar geoengineering can't affect El Nino or can't affect, in fact, I can imagine all sorts of ways that you could intentionally affect El Nino if you wanted to. If you really wanted to hit the Western Pacific hard or hit the Eastern Pacific hard, you can play all those sort of games. There's a wonderful paper that Elliot Zipperman wrote with Doug McMartin many years ago, arguing that you could control El Nino if you actually controlled the Western point and adjusted the warming there. So maybe you could control El Nino if you actually intended to, but the idea of an injection of sulfur, how that would affect El Nino, given the rapid timescale of mixing zonally, really hard to say. I'm not saying it will forever be that way, but at least for the foreseeable future, we don't have the tools to answer those questions, given the internal variability of the system, and frankly, the weakness of the models in simulating internal variability. There's another nice example, which is ship tracks. This is a map of the world showing all of the ships traveling across the oceans. As many of you know, for a long time, when we started banning sulfur from fuel in cars and trucks, the refineries put that into bunker fuel that was used in ships. So ships produce what are called ship tracks, which are essentially their smokestacks, put sulfate aerosols, sulfur dioxide into the atmosphere, which rapidly turns to sulfate aerosols and actually brightens clouds. And so you end up with essentially brighter clouds following the ships. And you can see this from space. And the highest density of ships is actually in the North Atlantic. So this is not like solar geoengineering. This is not using the stratosphere to mix things, at least hemispherically symmetrically. This is highly asymmetric. In 2020, we actually did this experiment. It's a little mini termination shock. We actually got rid of 80% of the sulfur in bunker fuel in ships. And so as a result, after 2020, in the last 5 years, we have essentially gotten rid of a lot of those ships tracks, and the Earth has warmed up. There are a variety of studies of this. Best, by the way, there's a couple from here from Oxford. I don't know if these people are here, but we can detect the perturbation and see that it actually changes clouds. And the best modeling studies say that the temperature change in response has been about 1/10 of a degree, maybe a little bit less. Jim Hansen says it's a lot more than that, but he's an anomaly. Everybody else seems to think it's between 0.05 and 0.1 degrees. And that it's about 3 times bigger in the Atlantic. But anywhere else, we can't say. Well within the natural variability. So here's a real experiment that was done in 2020, caused a warming instead of a cooling. And the answer is 5 years out, we really, other than sort of knowing what it did globally, and right over the Atlantic where the most of the signal was, we actually can say very little. So I'm not sure when we think about deploying solar geoengineering, at least right now, why we think we could say anything more than what its effect on global average temperature would be. I think that that's a reality that we have to face. And we have to be honest about that. Unfortunately, there's a lot of well-intentioned climate modelers who run a single model, tell you how it changes rainfall in pick a place, and think that that's a robust result. And in fact, if you looked at 6 different models, you get 6 different answers. It's just beyond the skill of the models. It's not solar geoengineering, it's climate change too. If you actually look at the reliability of climate forecasts from CMIP6 models at a regional scale, it's pretty low. Okay, I want to keep moving because I want to make sure we have time for questions and have a dialogue. So I want to talk about another concern that Ray has, which is there are some really significant ones here. I'm not going to read this whole thing, but if we're forced to stop, he says we're hit with dangerous withdrawal syndrome symptoms, a catastrophic termination shock, wherein a century of pent-up global heating emerges within a decade. Some proponents insist we can always stop if we don't like the result. Well, yes, we can stop, just like if you're being kept alive by a ventilator with no hope of a cure, you can turn it off and suffer the consequences. I think this analogy is interesting. Why is Ray doing? To me, this actually undermines his whole argument. If you're on a ventilator, it's true, you're stuck, you can't turn it off. But I'm not quite sure what Ray's trying to get us to think. Does that mean we shouldn't put the person on the ventilator in the first place? That's a strange analogy. I think the core of this disagreement is whether the Earth needs a ventilator, right? Not, to me, if somebody needs a ventilator, we should put them on a ventilator rather than let them die. He also says there are other effects of carbon pollution, such as ocean acidification, worsening over time. What I want to talk about is this kind of depiction. I had a workshop at Harvard. I was part of a workshop on the governance of solar geoengineering, and it was filled with political scientists from all over the world who were among the best experts in international relations, most of whom had never worked on climate or solar geoengineering at all. And their reaction to this issue made me realize that many of us in this community who talk about solar geoengineering have done exactly the same thing that Ray's doing. We actually are putting our values, mixing them up with what the science is. And I'll explain what I mean. So here is something, this comes from Doug McMartin. I think David Keith uses this also. And so the idea is, okay, here's business as usual, emissions going up. This is what would happen if we cut emissions aggressively. This is climate impacts, not CO2 in the atmosphere, but it's presumably correlated. This is what would happen if we removed CO2 from the atmosphere, and then solar geoengineering just sort of cuts the peak off, just reduces the impacts a little bit. This is an inherently defensive framing. And in fact, David Keith, Doug McMartin, I do the same thing. When I talk about solar geoengineering, I always say, oh, it's not a substitute for reducing emissions. You still have to reduce emissions. I often make an analogy to morphine. It's like if you're having a surgery, major abdominal surgery, doing it without anesthesia is a really bad idea. But just taking the morphine and not actually having the surgery is a really big mistake too. That's the analogy. I think it's wrong. And talking with some of these political scientists, I realized I'm putting my own values and maybe my own defensiveness about this in place of a clear scientific analysis of what's going on. So what I want to do with you guys today is just quickly ask this question. So for 2 decades, we've always emphasized that solar geoengineering is not a substitute for reducing emissions. But is that actually true? Remember, we don't get to decide whether we use this. This is going to happen at a big scale. So what would happen if the world deployed solar geoengineering and didn't work to eliminate fossil fuel consumption? So first thing that everybody mentions who doesn't like solar geoengineering is ocean acidification. And that's true. If you don't do anything about the CO2 and cool the climate, you're still going to have the CO2, and that's still going to acidify the ocean. The surface ocean. Ocean acidification is a mixing problem, a timescale problem. So here is Station Hot in Hawaii, Station Aloha, and what you see is carbon dioxide going up in Mauna Loa, and this is pH going down, measuring at Station Aloha. Okay, shock. That's what happens. And what you're seeing is a pH change from about 8.1 something down to like 8.06 or something like that. Okay, pretty small change, but it's still a big deal if you're in the ocean. I will add, although ocean acidification sounds scary, the actual impacts on us are largely still unknown. We know that it affects organisms that calcify, so corals are going to be affected, but corals are much more affected by the warming. It's the warming that's driving the bleaching of the corals more than anything else. I actually used to work on coral reefs a lot. And to me, saying we shouldn't do solar geoengineering because of ocean acidification is like saying, well, you shouldn't have lung surgery if you have lung cancer to remove a lung because you'll be short of breath. Like, that's missing the point. Let's keep going now. Sea level rise. To me, this is a much bigger deal. I don't see that solar geoengineering actually reduces sea level rise that much. It may reduce the rate a little bit, but it's not going to eliminate sea level rise. Now, sea level rise, because it occurs on a long time scale, never feels like an urgent problem to governments. But in the long run, it's going to be the thing that we're going to look back at, well, generations from now, they'll look back at us with horror because it's going to transform the Earth. Here is Grace data from Greenland. Greenland, the primary mode of melt loss, or of mass loss, is summer melting. So there's summer melting that's accelerating, melts more in the summer than snow adds in the winter, and that's the primary mechanism for mass loss, and certainly the primary one into the future as well. So presumably in Greenland, you could cool Greenland and stop summer melting. So solar geoengineering could work over Greenland to stop the loss of mass for Greenland. By the way, problem, geopolitical problem, I don't know how to cool Greenland and stop melting and not freeze Russia's northern ports where they built all this infrastructure for getting oil and gas out. Maybe we wouldn't need that oil and gas then, but I'm just saying Russians may not like it very much. That is, you can't just cool one spot, at least not right now. Antarctica, though, is a different story. So this is the pattern of mass loss in Antarctica. And in Antarctica, it's important to remember this isn't driven by melting. Most of Antarctica is so cold, it's well below the freezing point. You could warm Antarctica 6 degrees and most of it would still be frozen. The mechanism of mass loss in Antarctica is primarily actual physical sliding of ice into the ocean. So here's the Thwaites Glacier, which has been the focus of attention for the last decade, but there are other systems there that are vulnerable as well. You have an ice shelf that's breaking off primarily because of ocean warming, distributed ocean warming, getting under the ice shelf and eating it away. And there's a grounding line here. And the concern is if you pass this threshold, if it retreats, if the ice shelf breaks off and it retreats past here, at that point, it's just the physics of ice shelf collapse, of ice cliff collapse. The glacier is going to flow into the ocean. Estimates are once you pass that, you're guaranteed to cause about 1.5 meters of sea level rise. And cooling isn't going to stop that. It's driven by gravity. So maybe you could engineer a giant blockade, but that's pretty big. It's important, though, that solar geoengineering doesn't fix that. Once you've uncorked the bottle, it's going to flow. Okay, so I think that's a big deal. But I think the biggest concern, and this is certainly, I think, Ray's and many people's as well, is that if we do solar geoengineering and everybody feels like the catastrophic risks of climate change are avoided, then we're not going to work very hard to reduce emissions. This is what's often called the moral hazard. You could see, he says in his Guardian article, it is laden in moral hazard, providing as it does an excuse for fossil fuel interests and their advocates to continue with business as usual. So what is the moral hazard here? Well, it's a terrible term. It actually comes from economics and it's a misapplication, so it's not a very good use of this. But what it refers to is the idea that stabilizing or reducing temperatures through solar geoengineering might weaken global commitment to cutting emissions and therefore lead to higher cumulative global emissions overall. So how big is it? If we pursued development of deployment of solar geoengineering, how much extra carbon dioxide would end up in the atmosphere? I think that's an important question to ask. And this kind of cartoon makes it seem like it's enormous. So here's the business as usual. Here's what happens if you cut aggressively. If you do this instead of this, that's a really big deal. And we often think about things with cartoons, but in this case, I think that's a really bad idea. So let's ask it this way. In the last few decades, how much of the reductions in the past few decades has actually been due to a concern about climate change? And I think what most people would agree is that it's actually pretty small. It's not zero, and it's really hard to quantify. But let's take Germany, which was in some ways the shining example of the very high feed-in tariffs starting in 2004 with the beginning of Energiewende. Those feed-in tariffs had a variety of factors, but the dominant ones were industrial policy. The German government thought that by building their solar manufacturers, they would be able to sell their products to the world. Turned out they didn't anticipate Chinese dominance in manufacturing, but it was a good try. It was good for the world. They were very concerned about energy security, their dependence on Russian gas. And of course, also the public hates nuclear in Germany. They essentially substituted solar for nuclear. Climate was on the list, but it was a distant fourth. If you think about EVs, for example, in China, and their investment in electric vehicles, driving factors, industrial policy for sure. They're selling EVs around the world now. I was just in Israel where every third car is a Chinese EV. Every third EV is a Chinese EV, maybe even half of the EV is sold there. And then energy security. China is the largest importer of oil in the world. They also are very concerned about air pollution and the health effects. Climate is on the list, but I think it's probably a distant fourth. Okay, so it's going to be hard to do this, and I need to wrap up relatively quickly. But I just want to be a little more specific about this moral hazard. Here are the scenarios used by the CMIP6 and the IPCC, the different types of scenarios. I don't need to go into details. I can tell you, though, that the purple is seems to me incredibly unlikely because it requires sustained economic growth in the face of unbelievable climate change, which doesn't seem plausible. And the green is pretty much out of bounds as well. We're somewhere between yellow and red. So if my friend Don Farmer, who's here at Oxford, is right, the technology transition is going to be driven by cost, by learning curves. What in this paper, Don argues that the drop in cost of solar and wind and batteries and everything else is going to drive the transition. I hope he's right. I worry that he's not, but I hope he's right. If he is, it's not a concern for climate, it's economics. So what you might say is a concern for climate might get us going in the initial investment period, the way German invested in solar, that sort of got things going. But again, as we saw, climate wasn't the motivation for that. I like this cartoon to summarize this. This is an actual cartoon from Vanity Fair from 1861, showing the whales celebrating the discovery of oil in Pennsylvania. This is not true, by the way. And I don't mean that the whales didn't actually have a ball. I mean that the idea that the discovery of oil was good for whales was not true. 20th century petroleum-powered whaling ships probably killed more whales in the 20th century than sailing ships in the 18th and 17th and 19th centuries. But that's a separate issue. The point of this is that we didn't stop whaling, say, in Massachusetts, where I live, because we cared about the whales. We stopped because there was an alternative to whale oil that was cheaper and better. That was petroleum. And I think that's important when we think about the energy transition too. One other small point, and this is just my geochemistry hat that I have to explain, that solar geoengineering is likely to enhance ocean carbon uptake as well. And that's because it reduces stratification as well as the impact of warming on solubility. This goes way back to 2001. This is an old IPCC figure of the carbon cycle. On the left, this is a calculation that they showed using a whole bunch of different ocean carbon models and just showing the range of different models. And then on the right, what they did is they took the average of these models and they ran it through another series of models to look at the climate effects. At the time, the models weren't capable of coupling these, and so they did it this way. But what's kind of nice about this calculation is you can see the climate effects, that is the impact of warming, separate from the basic mixing of higher CO2 in the atmosphere. And so what you see is that all of the models show a decrease by anywhere from 1 to 3 gigatons of carbon per year. And this is carbon, not CO2. Based relative to the mean of the ocean models with the CO2 only. And that's not a huge amount, but it's not tiny either. It could be, anywhere from, 3 to 10 gigatons of CO2 a year, which is not small. That is, essentially, solar geoengineering, if you actually cool the climate, it's going to make the ocean take up more carbon. That's interesting. You have to include that in that delta. And so when you actually look at these scenarios and you say, okay, what's the delta? If we're on the red curve, if that's our future, and I'm not going to try to predict the future of emissions, but I suspect it actually is going to look more like this with SRM, all things considered. Significant, but not up to the purple. Same with the yellow. With SRM, it's going to be something like that. I'm not saying that that's a qualitative analysis, but it's I think you can argue that it's a lot smaller than maybe our intuition suspects. And when you actually turn that into future CO2 concentrations, here's CO2 in the atmosphere, what you're talking about, instead of stabilizing at something like 550 ppm, you're talking about an increase in that stabilization of maybe 50, maybe 75 ppm of CO2. The higher number, maybe it's 100 or 150 ppm higher, which is a big deal. The big deal, though, to me, is what's not represented in any of these graphs, which is what happens in the out centuries. That is, to me, the long-term effect of solar geoengineering is that you don't have to do the really hard work to get the last third of CO2 out of the atmosphere, out of the emissions. That, in the long run, leads to really big problems. But really hard to get people to care about something that's 300 or 400 years away. So I'll just say that's a real concern. And so in terms of temperature, if you look at the differences here, we're talking about SRM in terms of the size of the moral hazard. We're talking about something that's probably less than ½ degree. Not zero, not zero, but it's not as big as the rhetoric sounds. I think the permanent risk of termination shock is there. I think if you start doing this, you have to do this forever. That's a burden of society. And to me, that's daunting. And we have to be all clear about that. That's what you're dealing with. You're dealing with a system that has really long timescales. And so if you're going to mitigate it, you're going to have to deal with really long timescales. The termination shock, as it's been simulated, it's important to remember, it doesn't happen in a year. It doesn't happen in 6 months. Because of the timescales of the ocean and the atmosphere, it's going to happen over 5 to 10 years. Meaning you probably have time to reverse it if you wanted. Not instantly. It's not going to happen in a few weeks. One final point I want to make, just because I think this is really something that's misunderstood about solar geoengineering, because we misunderstood it. when Ray is attacking a Harvard group, he doesn't mean me, he means David Keith, but maybe he means me now. Although I'm not doing aircraft design, but there were some people in David's group that were doing aircraft design, estimating it, and Ray doesn't think this is research. He thinks this is like heading towards deployment. I don't think he's right. Let me explain this. Historically, in 2008, Scott Barrett, who's an economist at Columbia, a wonderful guy, wrote this paper called The Incredible Economics of Solar Geoengineering. And that was basically that, this is, as he thought it was going to be a few $billion a year. A few $billion compared to a few $trillion a year for decarbonizing the planet is like free. And in general, that perception has persisted. David Keith and Jay Apt in 2012 estimated that it was going to be around $1 to $3 billion per year. Paper in 2016 said it might reach 10. Wake Smith, who's a former Boeing employee, and Gernot Wagner estimated a similar number. But this paper came out just a few years ago. Wake Smith wrote a new paper where he took a look at the old work he did and updated the numbers and was a little bit more careful about the engineering. And he concluded that it was going to be about 18 billion per year. I've had people who know a lot more about the costs of aeronautical things look at this, and they think he's actually being very conservative. It could be 4 or 5 times this much. People are notoriously bad at estimating what things cost. Maybe they'll be learning, if Stone Farmer's right, but I don't think you're going to learn that much on a government program to do solar geoengineering. 18 billion is a really different number from 3 billion. And here's why it matters. 18 billion, he's right. Suddenly, the discussion of having non-state actors do this, or even small states do this kind of randomly, that's not what we're talking about. At 20 billion a year, and it could well be 100 billion a year, at 100 billion a year, only the largest countries, and even the largest countries, probably wouldn't do this without some coordination and some contribution from other large countries in the world. That actually solves some of the governance concerns. I'm not saying we should be satisfied with this, but nobody's going to do this casually, and nobody's going to do this abruptly. What we're talking about to get this going is like 400 new aircraft that have never been built, ramp up costs of probably hundreds of billions of dollars, and probably a 5-year timescale to get it going. So this isn't something that somebody can just, let's try this tomorrow. I think it's important for us to understand this is a serious, expensive endeavor. So it's not cheap. It's still cheap compared to decarbonization, but it's not that cheap. And so if the higher costs estimates are correct, then there are really important implications for governments that we have to think about. Okay, so I'm going to stop, but how do I feel about solar geoengineering? I sort of have tried to keep my feelings hidden, although probably didn't do a very good job. Here's how I feel. This is a famous quote from Winston Churchill. It's been said that democracy is the worst form of government except all the others that have been tried. That's kind of how I feel about solar geoengineering. I think it's a terrible, arrogant, inappropriate response to dealing with climate change, except for the alternative, which is actually letting climate change proceed. And I personally believe it's likely that some world leader, or sorry, that's supposed to say or, not work, or group of world leaders will deploy some form of solar geoengineering this century, unless our ability to adapt to climate change is much better than I anticipate. And that's troubling for other reasons. The frog in the pot of boiling water that warms up slowly, that's a bad outcome, and that may be the case. It may be that the impacts of climate change never shock anybody, and it's never worth spending $100 billion a year on this. As scholars, I feel like it's our obligation to try to understand this as much as possible, including all of the ways it could fail, because that might actually influence decisions in the future of how people might use this. And I actually think it's really important. And when I ask, okay, why are Ray and I on such different sides of this? It's almost like my old friend and I can't even have a conversation about this. I come to this part, which is at the end of his Guardian piece. He says, Bill Gates insists that renewable energy is inadequate to decarbonize our economy. Peer-reviewed research suggests he's wrong about that. The peer-reviewed research he's talking about is this, papers by Mark Jacobson, this one in particular, in PNAS, about how we can, in the US, get 100% of our energy from wind, water, and solar for all purposes. He wrote this paper a while ago, and this is, in fact, the link from the Guardian piece that Ray wrote. Shortly afterwards, this paper was published. This is by Clack and others, but if you actually look at the authors, they're from all over the US, and they're from all different types of people. Dan Kamen at Berkeley, Jay Apt at Carnegie Mellon, Ken Caldera. Many people, they don't agree on almost anything, these authors, except they all agree that this paper is rubbish. This is the biggest, if you actually read this paper by Clack, it's like the biggest smackdown I've ever seen in science. It basically said, this is garbage. And so what Mark Jacobson did is he turned around and sued them and sued the National Academy of Sciences. This is, yeah. Anyway, he actually put in a $10 million lawsuit. Eventually, a few years later, he dropped it. This is the LA Times article announcing that he finally dropped his lawsuit against the National Academy of Sciences for publishing a peer-reviewed paper. And he actually was ordered to pay legal fees of the people he sued. So I'll stop here because I'd love to have a conversation and see how your reaction to all of this is. I'm continuing to evolve. My thinking on this is continuing to evolve. But I would say right now, all of the studies suggest that solar geoengineering can be used to reduce warming from climate change. And that the regional impacts, I think it's important to understand they're likely to be unknowable beyond the general warming trend that has a spatial pattern, both in terms of detection and in terms of forecasting. I think we need to be clear that solar geoengineering may indeed be a substitute for reducing emissions. That is, from future leaders' perspectives, just saying it is not good enough. We have to say, if you do it and you don't reduce emissions, here's what is going to happen. That doesn't mean that emissions is going to grow indefinitely. I think there's something true about what Don is saying about the dropping cost of clean energy. However, the risk of termination shock is real and commits us to doing solar geoengineering indefinitely. And if you ask me as a geologist when my biggest concerns are, it's out in the distant future. It's not in the next 100 or 200 years. It is cheap relative to rebuilding our energy system, but it appears to be a lot more expensive than we originally imagined. And a lot of us thought, oh, it's essentially free. We don't need to worry about the cost. There is, I got to tell you, I get a little bit of personal reassurance or comfort in the fact that it's 100 billion or 20 billion and not 2 billion a year. I think it's actually a little better for us that it's a little more expensive because we're going to do it a little more carefully and a little more methodically. Again, the Winston Churchill quote captures how I feel about it. To me, solar geoengineering sounds like science fiction. It sounds like a nightmare, but unfortunately, the impacts of climate change are real. So I'll stop there and would love to have a conversation. Thank you.
Thank you, Dan. That was fantastic. I've got lots of questions, inevitably, but I don't want to. I want to get questions from the room, but needless to say, I have some in reserve. But who wants to kick off the questions? Okay, let's fire away. How many have we got? Some. So shall I take that one? In the middle, of course, inevitably, right in the middle. Sorry, Helen. Is there a spare mic as well? Yeah, okay, great. So we might get two on the go. So somebody else put a hand up if they want to be the next question. We can get the mic over to you, Steve. Yeah, great. Okay, fire away.
Thank you so much. I really enjoyed that and learned a lot. But I feel like you teased us with this quality of unknowingness or unknowability and you sort of buried the lead, I thought, in point 2. This question about important implications for governance to me is like the whole story. And actually what you laid out very clearly is that we know, I mean, you convinced me that the unknowability of the regional impacts of SRM is knowable, is something we can be pretty certain about.
No, it's not knowable.
No, the fact that it's not knowable is knowable.
That's what I
think
mean.
that's what you're saying
that's what
here.
I'm saying. We know that we
Yep.
can't know the impacts, and that has political effects from the start, right? No matter what happens, it's possible for different actors to claim effects which can't be determined. There's no way to adjudicate this, but we can be clear that people will disagree, and there will be significant political effects of that, which is part of this system that you're describing. So I'm just wondering, what are your thoughts on this? You know, you sort of have this has important implications for governance. Can you tell me a little bit more about how you think about that?
Yeah. So I mentioned this workshop with all these political scientists, and they shocked the hell out of me because I always thought governance was the biggest issue, as did many of my colleagues at the Kennedy School. And these political scientists came in and they said, we don't see a governance problem here. Everybody seems to be a winner. You don't really know if there's any losers, or if there are, you won't know who they are. So what's the big deal here? This is a political problem. This isn't a governance problem. This is easy. I was like, wow, that's a different reaction than I thought. So it turns out that I think the importance of not being able to say, oh, if we do this, most people will be helped, but Indonesia will become a desert, and lots of people in Indonesia will suffer. I think if it was that situation, you'd have a whole complex negotiation about compensation, who has the right to do this, et cetera, et cetera. I'm not saying there won't be any losers. A paper recently that David Keith's group published, they did an analysis of grid points in some climate model and said 7% of grid points are adversely affected in a solar geoengineering, whereas 93% of the grid points are helped. Okay, now the problem with that is if you did another model, maybe you get the same result, but it would be a different 7%. Those grid points would be somewhere else. What I'm saying is, given what we are currently able to say about regional climate in general, the answer is you don't know. And it would take you probably 50 or 100 years of observations before you'd be able to affirmatively point the finger and say, this is what it did. And in terms of international negotiations and discussions of getting this thing off the ground, I suspect that makes it easier. Does that mean that people won't accuse whoever's running this of causing a storm or a drought, which happens anyway? The answer is, of course they will. Everything will get blamed. I didn't talk about it in this talk, but there's a huge bias towards errors of commission versus errors of omission. So whoever is in charge of this system is going to get blamed for everything. But it's important as scientists that we rigorously step back and say, can you actually know this? And I think the answer is you cannot demonstrate this. And that's like, I think that's important.
There's at least one person in the room who would disagree with you on that. I suspect possibly more. Yes, we can't know it with CMIP type experiments, but we can't know a lot with CMIP type experiments, but that doesn't exhaust the type of experiments we can do.
Absolutely.
And by the way, you also mentioned a case, that the Russia ports example, which I think is a real concern. And you might say, well, Russia doesn't deserve those ports because they shouldn't have warmed up the climate with all those emissions. But the point is, they've got them now. And so this whole problem about what the counterfactual is, when people are arguing about the impacts of geoengineering, some people might quite like the warming.
So there are many aspects of the problem that I didn't have time to mention. For example, who gets to decide how much we cool? I mean, for example, if your goal is to stop Greenland from melting, you have to cool it a fair amount because it's melting every summer. So you can't keep things the way they are today, 1.5 degrees warming, because we'll lose Greenland. So you have to cool it much more. I kind of like the warmer winters. I mean, it happens to have been a cold winter in Boston this year, but in general, Boston is much more livable than it was 100 years ago. I don't want to go back 100 years. We're adapted to this climate. But talk to farmers. They don't want to go back 100 years of climate. They're adapted to this climate. So figuring out how to make those decisions, really complicated. There are lots of, not necessarily losers, but losers, that is, we've all adjusted to the current world we live in. If we really want to stop some of the long-term impacts of climate change, the thawing of the permafrost in Siberia, for example, we can't keep things stable at 1.5 degrees. We have to go backwards. That's going to be unpopular. So it's complicated.
Yeah. Steve.
Yeah, thank you. Really enjoyed that talk. So for background, I'm an associate professor in greenhouse gas removal. So I look at the CDR side of this, and I love coming to SRM talks and inserting CDR in some of the statements and see how they would change it, whether I'd agree or disagree, and vice versa. But I guess I'd love you to unpack your argument a bit about the effectiveness of climate policy, because I'm not sure I quite got it. You kind of, I know you had to skim over things quickly, but you kind of said, well, climate policy doesn't work. Okay, maybe Germany reduced their emissions, but they did them for other reasons. And I can kind of sympathize in a US context with a kind of lack of belief that climate policy has worked. But just to stick up for it a bit, I think the stats show that nearly 30 countries have already peaked their emissions and are coming down. And that's true if you look at a domestic production of emissions or a consumption basis. So it's not just an offshoring argument. And to take the UK as an example, we switched off our last coal power station last year, and I'm pretty darn confident. It's really hard to quantify, but that wouldn't have happened without some form of climate policy and a combination of air quality.
That's probably true for the last coal plant, but let's be honest. You got rid of coal starting with Margaret Thatcher.
And Margaret
Thatcher did it. It had nothing to do with climate. It had to do with labor. Then the big thing that pushed all of Europe down decarbonization that's been happening for 50 years is North Sea gas. North Sea gas replaced coal. That's by far the biggest factor. And more recently, you have the growth in renewables. But again, a lot of that's driven by economics. I agree, climate is a factor, but it's a much smaller factor. You surely couldn't say that overall reduction in emissions in the UK is primarily due to climate. I don't think that's true.
So yeah, so to pick on that thread, I mean, a lot of people here in Oxford would complain actually that renewables are expensive, but we still did them. So it's not always a pure economic rational argument. But if I were to buy your argument, if I were to buy your argument, I think you were then saying, well, with solar geoengineering, it's going to be expensive, but a country or a group of countries will do it in the future. And for me, there is no so what would be the benefit of them doing it if the sole benefit is to fix the climate, and if we're not doing that now? I'm trying to understand what the logic is there.
What I'm asking there is the question: if you did solar geoengineering, the only reason to do solar geoengineering is because you're concerned about the catastrophic effects of climate, right? The question is, the moral hazard is, if you did that, then CO2 emissions are going to keep growing and you're not going to reduce emissions. I'm questioning that argument. I'm saying, how big is that effect? And I suspect that effect is smaller than we think it is for a couple of reasons. One, that a lot of the driver for switching to clean energy is not climate, is other things. You're still going to have energy security issues. China's still going to be we're going to switch to EV. The world's going to switch to EVs. It has nothing to do with climate, whether you care about climate or not. If you remove climate from the equation, we're going to switch to EVs because it's a better technology. But here's the interesting question, which is, if you, so the question is, how much higher would it be if you didn't, if you no longer cared about climate? By the way, there's some people who make an argument, and I don't know how to evaluate this argument. They say that if we actually did solar geoengineering, people would care more about climate, and they would actually reduce their emissions faster because of the scariness of this system. I don't know how to evaluate that, but that's an argument that's been made as well. I'm making a slightly different argument, which is just that the delta of suddenly saying, okay, we've stabilized the climate with solar geoengineering. So what's the moral hazard of us continuing to do more emissions because now we're not going to pay the consequences in terms of climate? I actually think they're absolutely real, but they're quantitatively a lot smaller than what you imagine from these sort of schematic figures.
So just if I get your argument right, it's kind of either we take climate change seriously enough as a world that both reducing emissions and doing solar geoengineering probably makes sense, or we do neither.
I think that's misstating it a little bit. Eventually, we will take climate change seriously because the impacts will be too severe. But I think the path to reducing emissions, given that it's a global collective action problem, is climate is one of many factors that we use for making large investments in energy systems. And I would say cost, security, and economic opportunities are probably on short timescales more important if you look at governments and even people. And I think that's what I would say.
I just want to say this is killing me to try and share this, but Tim, I can't jump in on everyone.
Dan, I wanted to just kind of reiterate a point that Miles glossed over a little bit quickly. And, you know, I'm trying to separate out the politics and the science and focus on the science. And your statement too about the impacts being unknowable, I mean, as I understood it from your talk, that was on the basis of taking a few CMIT models and showing how much they disagreed regionally. And you know, the question is that telling us that the impact is unknowable, or is it just telling us that our current state of climate modeling is woefully inadequate? And I would argue for the latter. I mean, we can see this if we just look at many of the trends in climate in the last few decades and how well they're simulated in CMIT models. ENSO is a really good example, but there are many others. And the answer is they're not. And, you know, I think Miles and I both said if CMIT was ever used to do weather forecasting, people would realize how woefully poor they are.
Absolutely.
So the question for me is, I mean, I'm prepared to take your statement as an interesting science question. Are they knowable or unknowable? I mean, perhaps we don't know. But my feeling is that which I would say we do, if we feel that these climate models are an important part of informing policy, whether it's climate change, mitigation, adaptation, or solar engineering, we have to somehow, as a community, move beyond the current CMIT paradigms, which everything seems to be based on these days, because they're not serving us well. And the systematic errors in both in the mean state and in the internal variability are just massive in these models.
Yep.
But, you know, it's at the end of the day, it's Navier-Stokes and laws of thermodynamics, and that doesn't intrinsically make the notion that if you apply a forcing, it's unknowable. It doesn't imply that from the basic theoretical equations.
I think that's right. I think that detection of it is really hard, given the internal variability is so large, right? So again, our ability to say something is not so easy. And I also think it's important to look at things like the paper I just flashed that Terry Manuel and Gabe Becky did, where they embedded a high resolution model in. And there's all sorts of different ways of doing that. You could do that with an ECMWF model. And the question is, what would you see? And do the experiment. What these guys saw is that the impacts of warming were reduced when you actually geoengineered. I suspect that first order effect of reducing the warming, which we know it does, probably dominates over everything else. That isn't to say there won't be some regional effects. I think there are, but I think we need to think about mechanisms.
Right, but
and second,
yeah.
I suspect that rising above the signal to noise is really hard.
Yeah, but you know, if we take Ray's and Michael Mann's point, you know, are we going to increase drought in parts of the world? Well, the first thing, if you have a model, you're going to address that question. The model has to be able to produce droughts. You know, and most climate models actually don't produce droughts.
Right.
Look at the South African drought. They don't do a good job at that. So I think your point too is at the moment debatable, I would say, and it's important for science to address it, because that's a really basic scientific question.
And I would chat like, so let's try to figure out whether this is true or not. I would say based on what we have, the tools we have right now, it's essentially unknowable. I think it's based on our current generation of tools. But I would say even the claim that, you know, oh, solar geoengineering might cause some drought, a lot of people get this wrong. It has to be relative to what? And it's not relative to the climate we have today. That's a choice we're not being granted. Our choice is to either do solar geoengineering or to not do it. Either way, the climate's going to warm, and I suspect it's going to warm a lot. And so it's not whether the solar geoengineering world creates droughts, it's whether they create droughts that are worse than the droughts that would happen in a warmer world. And that's a really important subtlety that a lot of people miss, but it's really important.
Question at the back there.
Andrew Lockley. I wanted to ask if you're in a situation where the regional climate impacts are inherently unknowable with the current generation of models, and they're also undetectable for decades later, how can you have a meaningful discussion about the political advantages and benefits and the human impacts and the decision-making process that you've got to go through if you're basically shooting in the dark, and you're shooting in the dark at people you can't tell whether you've shot, even when you've shot them?
I think the answer is we know that this would reduce global temperatures, average. And to first order, that means it's going to reduce whatever the impacts you're afraid of climate change. This will make them less. That's what we know based on everything, all the calculations that have been done so far. And yes, it obviously comes with a risk of some regional effects that we aren't able to simulate because the models aren't good enough. We can't do it reliably. What I was trying to argue was that actually that makes governance a little bit easier. That is, if you're a government, you're suffering from impacts of climate change, you're worried about the warming that's going to happen in the future. I don't think you do this casually, but I think you probably look at all of the information we have and say, this world looks like a lot better. A geoengineered world looks a lot better than the one without. I don't think we're going to be doing this until people are pretty unhappy with the impacts of climate change. But I also think the impacts of climate change are coming. We're just getting started. Miles knows this. I'm much more doubtful that we're going to come anywhere close to the yellow trajectory on that curve and that IPCC scenario. And I think we may well have 4 degrees before the end of the century. I think that's going to hurt a lot of people.
I was just saying that some of us are really convinced we're going to do a much better than CMIP style experiments at establishing what the actual impacts of climate change and, if it was ever done, geoengineering on weather events than we do at the moment. So
God's work. That's wonderful.
Hmm?
That's wonderful.
We've got to do the work, and it's not been done yet. So I would accept it's hypothetical science, but I do think I just want to reiterate Tim's point that characterizing the state of climate science as the state of CMIP, it's fair, but it hurts. And you know, we as a community we can do better. But anyway, I'm the chair, so I can't.
But thus far, you know, things like Kerry Manuel's and Gabe Becky's paper, where they actually embedded a high resolution model in, is interesting. And what they found was, lo and behold, the solar geoengineered world was much preferable to the just warmer world.
For the particular diagnostic they were looking at.
That's right.
And of course, that doesn't mean that there isn't somewhere else in the world where somebody's unhappy.
So we have to go do that work.
Yeah, exactly. We will get it, and we will here in Oxford, and other places as well. But it is something we care about a lot here. Sorry, there's another question at the back. Yes, thank you. And sorry, I'd already said, sorry, we'll come back to you at the back. Yeah, far away.
So I wanted to ask quickly about the cost of geoengineering. So you said that the high cost is reassuring, and I agree in some sense. But on the other hand, it means that any implementation of SRM is going to be controlled by one very wealthy country or a small collection of very wealthy countries. Particularly given how we've seen very wealthy countries recently acting in ways that are, not necessarily in the interest of
any wealthy countries you're thinking about?
Of the global community, not naming any particular countries. Does that how do you respond to that worry? Do you think it's valid but not as big of a problem as the alternative?
Okay, so I'm going to answer this, but not as me, Dan Schrag, who has my own opinions about politics and about the world. Let me be very clear. I have very strong opinions. I'm not going to answer it that way, though. I'm going to try to be a scientist and look at the world and say that I fear that many in the environmental community have been very naive about how real decisions in the world have gotten made. Global inequality is absurd. It's ridiculous. All of climate, when I hear the word climate justice, it makes me angry because I call it climate injustice because climate justice is an oxymoron. It's the most ridiculous, unfair thing in the world. All of sub-Saharan Africa, if you take out South Africa, all of sub-Saharan Africa has contributed 0.6% to global emissions, and half of that's from Nigeria. So the idea of telling countries in sub-Saharan Africa that they need to reduce their emissions is grotesque, right, from a fairness perspective. And yet, we need to do it. So this is a really, difficult situation. I believe the most likely scenario for solar geoengineering to happen is for some superpower, and the current superpower from whom I have a passport, I suspect won't be a superpower in 50 years. So I don't know who's going to be in charge, but I would be paying a lot of attention to China right now. But I don't know who's going to be the superpowers. I suspect, though, that the cost, if it's not 20 billion, but it's 100 billion a year, first of all, that brings in the question of space, because 100 billion a year, space systems people say they might cost a few $1 trillion, or maybe even $5 or $10 trillion. But if you amortize that over 30 or 40 years, suddenly that's back in the ballgame. But at 100 billion a year, if the US were to, I don't think the US would pay 100 billion a year for a solar geoengineering system without asking Europe to chip in a share. And if Europe chips in a share, then guess what? Europe gets to at least have a say or be at the table. Does that mean that it's the way that I would design it if I were emperor of the world, where a lot of poor countries would have some say in what happens? No, it's not. It's not. It doesn't seem moral to me. It doesn't seem right. But look at the world we live in. The world is ridiculously unfair if you look at just basic inequality. So I'm not saying that this is the way I want this to happen, but I suspect, the only people who are going to do this are superpowers. Although that gives me some reassurance to a world where a small country could do this arbitrarily with a cost of $2 billion a year. That's a very scary world. So.
Last question. Was it Callum? Yeah.
Yeah, thanks very much for the thought-provoking talk. I'm just interested in this question of who ends up being in charge, because one of the things that you're very sure about in this talk is that temperatures would reduce. But the thing you sort of skirted over a little bit was the fact of this termination shock. And I'm wondering, given sort of historical commitment to climate policy by superpowers, which waxes and wanes, I think that's quite a big risk. That assumption that it would reduce temperatures in the long term, given the governance by superpowers.
Yeah. So I mean, I think I didn't talk about it very much, but I did show you that graph. It's about a 10-year termination shock occurs over about a decade. I think there's
in temperature. I think in the hydrological cycle, it's a bit faster. But anyway, we can talk over.
It doesn't really matter. Okay. The point is that let's imagine a situation where a country collapses. Say the U.S. goes through a total economic collapse, and it was doing solar geoengineering, and everybody else was paying up. There's time for the rest of the world to figure out if they want to replace it. Maybe not perfectly, but again, the anomalies we're talking about, 0.5 degree, 1 degree anomaly. I mean, you could imagine all sorts of things. The reality is, do we think world leaders faced with really devastating impacts of climate change, say 50 years in the future, do we think the long-term commitment to doing this would make them decide not to do it? That's the question. I think they might pause, but it depends on what those climate impacts are. And I think the climate impacts of 3 or 4 degrees are going to be spectacular. I think we're just getting warmed up, so to speak. So, the other alternative is the one I said, that this never gets deployed because adaptation in most rich countries is fast enough that they don't feel that this is in their interests. That the agricultural impacts never get to be so catastrophic, and we continue to be able to feed the world and everything's okay. And unfortunately, in some ways, that's the cruelest world, because if you think about the developing countries of the world, they're probably most benefited by this because they're the most vulnerable to climate change. I'm not saying that it's right that they're not likely to have much of a say in this. They're not likely to have any control. They don't have much control in the world economic system today. But if we don't do this, I suspect that the poor countries of the world are going to suffer tremendously, a lot more than the rich countries. We can buy air conditioners. In India, 10% of households have air conditioners, and it's less in Sri Lanka and Pakistan and Bangladesh. And I think that's just important for us to realize. Now, it sounds very colonial saying this is better for them, but I actually think that may be true.
Dan, you've given us a fantastically stimulating lecture. I suspect this Q&A session would go on
Can I ask you
indefinitely.
one question before we end?
Sure, you get to ask questions.
You are also a good friend of Ray's, and I'm an old friend of Ray's.
Yeah.
What would Ray say if he were here? He sent you an email, and so I
Ray,
want to know.
I'm sure I'm going to hear about it, and I should say, I don't know where the camera is. Apologies to Ray for not representing you, so to speak. We differ for different reasons. You know, I think Tim and I differ on your point too. I think you've given us a lot of what Ray thinks about this, and I don't think he's changed his mind on any of those fundamental points. I mean, this, yeah.
You don't want to
I'm going to abuse. I certainly don't want to channel Ray. I didn't. That would be appropriate. But I think maybe we should perhaps get OCRN. Perhaps could get Ray and me, and maybe you join us on Zoom or something, and we have a conversation about it before in the not too distant future. That sounds like an interesting challenge, and bring some other disciplines in as well, because perhaps there's too much of this happening among earth scientists, as you say, I was really intrigued by what you were saying about the political scientists' reaction to this and so on. We need to get those perspectives in, which of course is what OCRN is all about, getting different disciplines involved in these conversations. Anyway, we have an opportunity to continue the conversation over drinks. So let's conclude by thanking Dan for an amazingly stimulating lecture. This is exactly what conversations in Oxford should be all about. Thank you, Dan.
Please join us for drinks outside, just to your right outside.
Thank you. As you say. Well, sorry, I thought maybe it's not what we're doing. Is to address this unknowability. I think the unknowability question, I think you're right. I think with the right design, we could pin down the impacts of solar geoengineering on specific